Okay, in this lesson, we're going to talk about double and half angle identities. And these are simply two new sets of identities that give us an opportunity to find the values of double angles. Like if we know the sine of 30, we can use this to find the sine of 60, or the cosine, given the cosine of 45 to find the cosine of 90. And we know that we actually already know the values of the cosine of 60 and the sine of 90 and all these other values. So the double and half angles are usually used when solving equations or like the first problems that we're going to work here. But again, these are simply two new sets of formulas, double and half angles. We'll talk about half in just a second. But we're going to start out with problems that are very similar to some problems that we worked in the last lesson. It says on number one, if the sine of theta is 5/13, then pretty much what's the cosine of double that angle? Now, we could go through the process of actually finding the angle first. We could move our sine value over by doing an inverse sine. And actually, once we find that angle, simply plugging it in here, doubling it, and finding the cosine of that angle. But we're going to go through this process and actually do it without ever finding the angle. So let's start out with a cosine of 2 theta. We're going to start with any of the three. Notice there's actually three different formulas that fits this. And since we're only given a sine value, it'd be kind of silly to use the one that involves cosines and sines, or also even the one that involves just cosines. What we're going to do is use this second formula right here that we can simply plug our sine value into. Now, I do want to remind you that in this formula, this sine squared theta actually means the sine of theta all squared. There we go. Well, that's just a notation for that value. So we know what the sine of theta is. We're simply going to plug that in, and after we plug it in, we will end up squaring it. So let me go ahead and erase that. Let's go ahead and plug that value in. We now have 1 minus 2 times the sine of theta was 5/13, which was given to us. We're going to square that. Now notice it does give us the quadrant of theta. We're between 0 and this is 90 degrees. And anytime we're between 0 and 90, this is just another way of telling us that we're in the first quadrant. Now before they would just come out and say, hey, you're in this quadrant. But now they're going to start using this new notation to tell us what quadrant we're in. Now that we've got it plugged in, we're simply going to use order of operations and clean this up. So we now have, let me zoom in a little bit. We have now 1 minus 2, 5/13 squared. We're simply squaring the top and squaring the bottom. That'll be 25 over 169. We are going to multiply 2 times that 25 over 169 by multiplying tops and bottoms. And that gives us 1 minus 50 over 169. In order to subtract those, we do need a common denominator. 1, we're going to write as 169 out of 169. And once we subtract it, we have a value of 119 out of 169, and that's going to be our final answer. So again, what you have just found, given that we have some angle whose sine value in the first quadrant is 5/13, the cosine of double that angle is going to be 119 out of 169. And we actually, we could kind of do some thinking on it. We're going to remain with this cosine value. Obviously, we're still in that first quadrant, because if we'd have doubled it and ended up in the second quadrant, our cosine value would have actually been negative. So our angle was small enough, less than 45 degrees, to where that when we double it, we actually stayed in that first quadrant. Number 2, we're asked to find the tangent of 2 theta. And again, the first thing we do is we go up and we find the formula that we're going to use, which is 2 tan over 1 minus tan squared. So let's go ahead and write that down. And then we're going to look at what we're actually given. So we're given that the cosine of some angle is negative 7 over 25. Theta is, and it tells us right here, this is simply saying theta is between pi, which is 180, and 3 pi over 2, which is 270. So if we're between, and let me kind of sketch this out because we'll need it. If we're between 180, which is right here, and 270, which is right here, that obviously means that we're in the third quadrant. all students take calculus. The only thing that's going to be positive is going to be our tangent value. Now notice for our formula, we're going to actually have to have tan values to be able to plug that in, but we're given cosine values. So we're going to, again, use the method that we had yesterday or in the previous lesson. We're going to draw our angle there in the third quadrant. We know that cosine is adjacent over hypotenuse. And you can use Pythagorean theorem there, 7 squared plus b squared equals 25 squared, or that's actually a triple. That's a 7, 24, 25 right triangle. And since we are in the third quadrant, notice that tangent is positive. So our value of tangent, which is what we're going to need for our formula, would be opposite over adjacent, which would be a positive 24 over 7. So that's what we're going to need to plug into our formula. So we now have on top 2 times 24 over 7. On bottom, we have 1 minus 24 over 7. And since it's tan squared, we do have to square that. On top, to multiply these two fractions, we're going to multiply the tops, which gives me 48, multiply the bottoms, which gives me 7. On bottom, we have 1 minus 24 over 7 squared. We're going to square each of them. Let's see, that's going to give me 480 and 96. I believe that'd be 576 over 7 squared, which is 49. Let me clean that up just a little bit. On bottom, we will have to subtract those, so we will need a common denominator. The 1, I'm going to turn into 49 out of 49, so now they can be subtracted. So on top, we're going to leave our 48 over 7. On bottom, we now have negative 527 over 49. And again, we have what we call we have a complex fraction. So what we're going to do, again, this is the division. So to divide two fractions, we're going to flip the second one and multiply. So we now have 48 over 7 times 49 over negative 527. Let me change colors here while I cross cancel these. The 7 and the 49 will cancel, leaves me with a 1. Scroll up just a little bit. Leaves me with a 1 and a 7. And that's all the cross canceling we've got. So that will give us a 336 on top, a 527 on bottom, and that negative sign I'm going to move out front. So my value for tangent, the tangent of 2 theta, will be negative 336 over 527. Number 3, doing the exact same thing. We're given tangent here. We're also given that my angle is between 90 and 180, which tells me I'm in the second quadrant. We're asked to find the cosine of 2 theta. And to find the cosine of 2 theta, again, we can use any of these 3 double angles. Let's look at what we're given. Since we're given tangent, really it doesn't matter which of the 3 we use. And just to be different, let's go ahead and use that first one. We'll do cosine of 2 theta is equal to cosine squared theta, or the cosine of theta all squared, minus sine squared theta. That's probably the easiest one to remember out of the 3 because it looks a lot like one of your Pythagorean identities. So we're given the tangent of theta. Let me draw it. We're given that the tangent of theta is negative 20 over 21 and that we are in, let's see, between 90 and 180. We're in the second quadrant. So let's draw this, draw it to my x-axis so that here's my reference angle. Tangent is opposite over adjacent. And again, they've given us a Pythagorean triple, 20, 21, 29 will be our hypotenuse. And again, you can use Pythagorean theorem if you did not know that. So with that said, notice that in my formula, I'm going to need cosine and sine. I'm going to come over here and the sine of theta, all students take calculus. We're in the second quadrant, so sine is going to be positive. Sine is opposite over hypotenuse, which is 20 over 29. Cosine, all students take calculus. So again, sine is the only thing positive, so cosine is negative. Cosine is adjacent over hypotenuse, so it'll be 21 over 29. Really, the positives and negatives won't matter, though, because the squareds will take care of them. So we've got negative 21 over 29 as our cosine value. So we got to square it, minus our sine value is 20 over 29. And again, we have to square it. So we've got, again, negative 21 over 29, square the top, square the bottom, and square the negative, which is going to make it a positive. And you get 441 over 841 minus 20 over 29 squared. Square the top gives you 400. Square the bottom gives you the exact same 841. You already have a common denominator, so subtract the 2, and it gives you a value of 41 over 841, and that is your final answer. Okay, next up we have half angle identities. And again, it's just another set of identities. So if you know how to use identities, the process pretty much is the same for if I throw a new one at you. The only thing that is a little different here is we have a plus and minus that we will have to decide when we half an angle. Like, let's go ahead and address that. Let's say that I give you an angle that's between 90 and 180 degrees. When you half that angle, it halves where it's at. So if you were to take all three of these values and actually half all of them, if you have an angle between 90 and 180, half of that angle would be between 45 and 90. So your original angle being between 90 and 180 was actually in the second quadrant, but when you half it, if you're between 45 and 90 degrees, that's actually in the first quadrant. And you would have to decide whether you're finding sine, cosine, or tangent. Well, is that angle going to be, or is that value going to be positive, or is it going to be negative based on where it's at? So that's all we're going to do there. So let's start with our first problem here. We're asked to find the sine of theta over 2. So obviously we're going to use this first one right here. So in order to use it, again, we see that the only value we need to plug in is cosine, and that's actually what they're giving us. So really this information here won't be valuable to us because we're not having to find sine or tangent. So we are looking for sine of theta over 2. So if we're, well, actually we'll have to use the information here. If we've got an angle between 90 and 180, 90 to 180, and I'm going to write it like this as an interval. If we half that interval, we're going to be somewhere between 45 and 90, as I showed you a while ago. So we started out with an angle in the second quadrant, but when we half it, we are now in the first quadrant. Since we are looking for the sine of an angle in the first quadrant, let's draw that. All students take calculus, so that's going to have to be a positive value. So now all we have to do, don't worry about the negative, we're going to plug in. We have the square root of 1 minus, the cosine is negative 4/5, all divided by 2. Minus minus is a plus. We are going to need a common denominator there. 1 I'm going to write as 5 over 5 plus 4 over 5, all divided by 2. We can now add those two values together. So from here on out, it's just basic algebra. On top, I now have 9 over 5. We're going to divide it by 2. That's a complex fraction. In order to do a complex fraction, we're going to flip and multiply. That'll be 9 over 5 times 1 over 2. So it's going to be the square root of 9 on top, 10 on bottom. That can be split into the square root of 9 divided by the square root of 10. You can always split radicals when it's being multiplied or divided. That'll be 3 over root 10, which does need rationalizing. We're going to multiply top and bottom by root 10. And our final answer, we'll write it up here, will be 3 root 10 over 10. Number 5 says if the tangent, so we're given the tangent, is 2 root 6, and we are in the first quadrant. This is an angle between 0 and 90 degrees. So if you're between 0 and 90, let's go ahead and show you. If you're between 0 and 90, when you half that angle, you are now going to be between 0 and 45. So if you're in first quadrant, you half the angle, you're going to stay in that first quadrant. So our half angle is going to be in the first quadrant. We're looking for the cosine of theta over 2. Since we're looking for the cosine and we are in the first quadrant, everything's positive, so we really don't have to worry about the whole plus minus. But the cosine of theta over 2, let's scroll back up and let's look for that formula. The cosine of theta over 2 is very much like the sine. The only thing that changes is the sign, SIGN sign. So we have plus and minus the square root of 1 plus cosine of theta over 2. So let's go ahead and write that formula down. So now we're just going to plug in the information that we need. So the information that we do need is the cosine, but they give us the tangent. So since they give us tangent, we're going to have to do some work here. So let's go ahead and draw our angle here in the first quadrant. We're given that the tangent is 2 root 6. Now this one's slightly different because we don't have a bottom. That bottom would be 1. So tangent is opposite over adjacent. So that'd be, here's my reference angle, 2 root 6 over 1. That obviously is not a triple. So we are going to have to use Pythagorean theorem here. We have a squared plus b squared equals c squared in order to find that value of our hypotenuse. 1 squared is 1. To square 2 root 6, you're going to square each piece. When you square 2, it gives you 4. When you square the square root of 6, it gives you 6. So this would be 4 times 6, and I'm going to go ahead and clean that up, which is 24. So 1 plus 24 is 25 is equal to c squared. And then when you square root it, that gives you a positive or a negative 5. And we already know that since we're in the first quadrant, we'll deal with our positive 5 here. So we are looking for the cosine. So the cosine of my theta, which in this case is actually, cosine of my theta will be adjacent over hypotenuse, which is 1/5. So that's what we're going to plug in. We've already said that since we're in our first quadrant with our half angle, that our value is going to be positive. So we now have the square root of 1 plus 1/5 divided by 2. We're going to find a common denominator of 5. We're going to change our 1 into 5 over 5. So we now have the square root of 6/5 over 2. Make that 2 a 2 over 1. You now have a complex fraction. We're going to flip and multiply. And if you'd like to, you could actually just mark it out and flip and multiply here. So we now have the square root of 6 over 10. We're going to split that, and then we're going to rationalize it. That's root 6 over root 10. Multiply top and bottom by that root 10. And that'd be the square root of 60 over 10. Now we can go a step further here. The square root of 60, I believe, is going to clean up a little bit. We can split that into the square root of 4 times the square root of 15 just to clean it up. Square root of 4 is 2. We don't know what the square root of 15 is over 10. And then that 2 and 10 can actually reduce. That'll give us 1 on top, 1 root 15, and then a 5 on bottom. Okay, the next one. We're looking for the tangent of theta over 2. So let's go ahead and scroll back up and write down the formula for the tangent of theta over 2. So that's the only one we hadn't used. And you can kind of see where it comes from since tangent is sine over cosine. You can see the 1 minus cosine on top, the 1 plus cosine on bottom. And the 2's would actually cancel if you do that. So you can kind of see where it comes from. So let's go ahead and write down the formula for the tangent of theta over 2. So in order to plug into this formula, we're going to need cosine values. They give us sine values. So in order to find cosine given sine, let's sketch this out a little drawing. We are in my theta, which is what I'm looking for the cosine of. We're given the sine of the theta. My theta is between 180 and 270. So I'm somewhere in this third quadrant. So let's go ahead and sketch this out. Here's my reference angle. There's my right angle. We're given that the sine is 8 over 17, so that would be opposite over hypotenuse. And that also is a triple. That would be an 8, 15, 17 right triangle. So again, we're looking for a cosine value. So the cosine of theta, since you're in the third quadrant, all students take calculus. Tangent is positive, so cosine would be negative there. Cosine would be adjacent over hypotenuse, which is 15 over 17. And let's plug those values in. Before we do, though, let's try to determine whether we need to keep this plus sign or this minus sign. Since we're in the third quadrant, I like to do it like this. We're between 180 and 270 degrees. If we're looking for the tangent of half that angle, let's see where half that angle falls. That half of 180 would be 90, half of 270 would be 135. So we started out in the third quadrant, but when we half those angles, now we're somewhere between 90 and 135, which is actually in the second quadrant. So it says we're looking for a tangent of an angle in the second quadrant. Tangent in the second quadrant, all students, tangent would be negative. So therefore, we're going to keep our negative sign on this one. So let's leave that negative sign out front. We have on top 1 minus the cosine of theta, which we just found a while ago was negative 15 over 17. And that minus minus will actually make that a plus. And on bottom, we have 1 plus negative 15 over 17. So I'm just going to write that as 1 minus, because positive, negative would make that a minus. We do need common denominators on top and bottom, so we're going to change them both to the exact same thing. That's 17 out of 17. On top, I'm going to leave my negative square root. On top, I have 32 out of 17. On bottom, 17 minus 15 is 2 out of 17. Again, you have an improper fraction there, a complex fraction actually, and you're going to flip and multiply. So that's going to be times 17 over 2, which is kind of nice because that means the 17s will cancel and leaves me with 32 over 2. And I'm going to go ahead and write that down, but 32 over 2 is actually 16 when you divide it out. So this one comes out all nice and neat, and my final answer, negative square root of 16, would be negative 4. Okay, on the next set of problems, we're actually using these to prove identities. And again, with proofs, we always work with our more complicated side, and we try to turn it into our clean side. So on the first one, cosine squared, which we already recognize cosine squared, we're not going to can't do a whole lot with it, but this cosine 2 theta, we recognize it as a double angle identity. And we can change that into one of 3 different things. Just a reminder from up here at the top, cosine squared is equal to all 3 of these things, and you can change it to any of them. So I'm just going to go with the first one, and sometimes on these you might have to try a couple of different ways. Sometimes one way might be easier than another way. But we now have on the left side cosine squared theta minus, make sure you put it in parentheses because it's minus cosine of 2 theta, it's minus the whole thing. So this cosine squared minus sine squared is what it's equal to. So when you subtract, you got to subtract minus the whole. Let's go ahead and distribute that negative sign just to see what happens. We have now cosine squared theta minus cosine squared theta, negative will actually be plus sine squared. And that was a pretty easy identity because these cancel and leaves me with sine squared, and that does equal sine squared. Number 8, we're actually going to work with probably, I guess, the right side here to begin with. So I'm going to put an equal sign over here, the sine of 2 theta, and you can go back up to the top and see what that's equal to. And it's equal to, let's go ahead and write it as 2 times the sine of theta times the cosine of theta. And it's going to be hard to get to here from that. So what I'm going to actually do on this one is I'm going to work with both sides. I'm going to change colors here so we can see the other side because there's not a whole lot I can do with that right side. So cosine plus sine squared. In order to square this out, since it is a binomial, I have to FOIL it. I have to do, and you can list it twice if you want to. You can do cosine plus sine times cosine plus sine and actually distribute it out that way. But what it's going to give you is going to be cosine squared plus, and I'm going to go ahead and skip to, I'm going to combine my like terms as I'm going. So that'd be cosine squared plus 2 sine theta cosine theta plus sine squared theta, which is actually about, we've nearly to our identity already. cosine squared plus sine squared. That's one of the most basic Pythagorean identities that we have. Sine squared plus cosine squared will always equal 1. So what I did is I kind of grouped those together. So I now have 1 plus 2 sine theta cosine theta, which is what we actually have on the right side. And if you didn't even want to fool with this right side, if you just wanted to work with the left side here, if you notice, hey, 2 sine theta cosine theta, that's one of my identities. I know that that's equal to the sine of 2 theta. You could work it that way, and then that way you don't even have to touch the right side. Okay, number 9. Kind of obvious which side we're going to work with here. Not a whole lot we can do with the tangent. So we're going to try to change this right side to where it's equal to tangent. And I know on top, cosine 2 theta, we've got 3 different options of what to turn that into. The bottom, we're kind of limited. And we are going to go ahead, we're going to try to replace cosine of 2 theta with 1 minus 2 sine squared theta. On bottom, again, we're limited on what to do with sine of 2 theta. That is simply 2 times sine of theta times the cosine of theta. On top, I did notice that I really want to use one of the identities that has the 1 in it so that what's about to happen is going to happen. You have the minus in front of the parentheses. Let's go ahead and distribute that. That's going to be turn the 1 into a minus 1, turn the 2 into a plus 2. So there's what we have now. And this is what I wanted to happen. The 1's actually cancel out. And on bottom, we have 2 times sine of theta times the cosine of theta. So let's go ahead and rewrite that. So on top, we have 2 sine squareds. So 2 and then 2 different sines. And on bottom, we have 2 times the sine of theta times the cosine of theta. And we are headed in the right direction because now that we don't have plus or minus signs, we can actually cancel these pieces and cancel out the 2's. We have a sine times sine on top. So I'm going to actually just mark out the 2 and one of the signs on bottom. So now we have a sine left on top and a cosine left on bottom, and we know that actually sine over cosine does in fact equal tangent. So we have made it equal out to the left side. Okay, the last one of these. We have the sine of 2 theta is equal to 2 times tan over 1 plus tan squared. So this one's going to be a little bit trickier. But let me give you some advice. Anytime I'm dealing with proofs that involve tangent, I like to get everything in terms of sines and cosines. It just seems like it's so much easier to work with. So I'm going to work with this right side over here, 2 times tan, and I'm going to change my tangent to sine of theta over cosine of theta. On bottom, I'm going to do the exact same thing. I have 1 plus tangent squared is actually equal to sine squared over cosine squared, because that'd be tangent squared would be sine over cosine times sine over cosine, which would be sine squared over cosine squared. So now on top, I can multiply these out. I'm going to put my 2 over a 1, multiply tops, gives me 2 times sine of theta. On bottom, 1 times cosine of theta would just be cosine of theta. On bottom, I am going to find common denominators. The 1 I'm going to turn into cosine squared on bottom, cosine squared on top. So now I can add those together. So I've got cosine squared plus sine squared, and I'm just so it's more recognizable, I'm going to write that as sine squared plus cosine squared on top, and I've got cosine squared theta on bottom. Quick reminder from the last problem, sine squared plus cosine squared will always equal 1. So that turns my problem into 2 times the sine of theta over the cosine of theta, all over sine squared plus cosine squared is 1 over cosine squared. And again, you have a complex fraction here. So we're nearly where we want to be. So let's flip and multiply. So we have 2 sine theta over cosine theta times cosine squared over 1. Our cosines, this cosine will cancel with one of these cosines and leaves me with 2 sine theta cosine theta. And if you'll look at your double angle identities, that's actually equal to the sine of 2 theta, which is what we were trying to make it equal to. So therefore, we have proven that those two values are the same.